In the span of just a few months, Google's quantum computing team managed to do two things that the rest of the world is still trying to absorb. They proved, for the first time in history, that a quantum computer can solve a real-world scientific problem faster than any classical supercomputer on Earth. And then, almost immediately after, they published research suggesting that the encryption protecting most of the internet could be broken by a quantum machine far sooner, and with far fewer resources than anyone had calculated before. This is the story of those two moments, what they actually mean, and why the combined effect of both landing within months of each other has sent shockwaves through the worlds of science, cybersecurity, and finance in ways that are still echoing today. Neither development arrived quietly, and neither has been received without controversy, but together they represent a shift in what quantum computing means for the rest of the world that is genuinely difficult to overstate, and that carries consequences for anyone who uses the internet, stores sensitive data, or holds assets that rely on digital cryptography for their security. To understand what Google achieved, it helps to go back to where the story started. In 2019, Google announced something it called quantum supremacy, a demonstration using its Sycamore quantum processor, showing that its machine could complete a specific computation in roughly 200 seconds that would take even the most powerful classical supercomputer approximately 10,000 years. The result made headlines around the world, but it came with an enormous caveat that critics were quick to point out. The task Sycamore had performed was essentially a random sampling problem, a calculation with no real-world applications, designed specifically to be hard for classical computers and easy for quantum hardware. IBM pushed back hard, arguing the task could be completed by a classical machine in far less than 10,000 years with the right approach. The debate left the quantum community divided on what the milestone had actually proved, and it left the general public with a confused impression of just how close or how far practical quantum computing actually was. The criticism stung, and Google's quantum AI team took it seriously enough that they spent the next several years working specifically on results that could not be dismissed on the same grounds. They also spent those years improving Willow itself, refining the manufacturing processes used to fabricate qubits, developing better error correction techniques that allowed more qubits to be added without the error rate rising in proportion, and working toward the class of hardware that could eventually run the kinds of algorithms that would genuinely matter for science and industry rather than just for benchmarking competitions between labs. Google spent the next 6 years trying to answer that criticism. The result was a 105-qubit quantum processor called Willow and an algorithm called quantum echoes. Unlike the 2019 demonstration, quantum echoes was not built to perform a task chosen because quantum machines happen to find it easy. It computes what physicists call an out-of-time order correlator, a mathematical quantity that describes how quantum systems become chaotic over time, with direct applications in understanding molecular structures, magnetic materials, and even the physics of black holes. The key distinction researchers immediately pointed to was that the result is verifiable. Because the quantum echoes algorithm can be independently run on a different quantum computer or benchmarked directly against measurements taken from actual physical systems in nature, its output can be checked in a way that a random sampling calculation fundamentally cannot. The team published 5 separate papers documenting the result, which appeared in Nature in late October 2025, and then announced the breakthrough publicly on their official blog. T has made it, in the words of the research team, the first ever algorithm to achieve verifiable quantum advantage on real hardware, a phrase that carries a specific and carefully chosen meaning in the quantum computing field. The speed at which Willow ran quantum echoes was genuinely staggering. According to the published figures, the Willow processor completed the calculation approximately 13,000 times faster than the best classical supercomputers available today. Not on a contrived problem designed to favor quantum hardware, but on a genuine scientific task with real-world implications. Researchers used the algorithm to simulate the nuclear magnetic resonance behavior of organic molecules, the same kind of calculation that drug discovery. Programs and materials scientists rely on to model how molecules bind and interact at the quantum level. They verified the results by running the same OTOC protocol on actual nuclear spins in organic molecules at UC Berkeley's Pines Magnetic Resonance Center, confirming that what Willow computed on a chip matched what physical reality produced in a laboratory. Quantum computing-enhanced simulations of this kind could eventually help researchers design new medicines, improve battery materials, and develop novel substances by modeling their quantum mechanical behavior with a precision that even the largest classical supercomputers fundamentally cannot match, because they are simulating quantum reality using approximations rather than actual quantum operations. Scott Aronson, one of the most prominent and often skeptical voices in quantum computing research, described the quantum echoes result as a decent candidate for genuine verifiable quantum advantage, while noting that an even stronger standard would be an algorithm whose result could be checked directly by a classical computer rather than only by another quantum machine. The hedged praise from a researcher known for rigorously challenging quantum supremacy claims was itself treated by many in the field as a meaningful endorsement of how significant the achievement actually was. Aronson also noted that quantum echoes occupies an interesting middle ground between the purely artificial benchmarks of 2019 and the genuinely transformative applications researchers are still working toward, representing progress that is real and measurable without yet being the kind of thing that directly changes what is possible in chemistry, drug design, or cryptography right now, but that clearly points in the direction those applications will eventually come from. And then, less than 6 months later, a separate set of papers hit the scientific community with an entirely different kind of impact. In late March 2026, Google published a white paper alongside independent research from a startup called Oratomic, founded by researchers who had previously worked at Google Quantum AI and at Caltech. Both papers arrived at the same conclusion from different directions. The number of qubits needed to build a quantum computer capable of breaking widely used internet encryption protocols is significantly lower than the scientific consensus had previously assumed. For years, the accepted estimate had been that cracking elliptic curve cryptography, the mathematical system that protects the vast majority of secure internet traffic, would require a quantum machine with millions of stable qubits, a scale of hardware that seemed safely decades away. The new research revised that estimate sharply downward, with Oratomic's paper suggesting the threshold could be as low as 10,000 qubits rather than millions, and AI tools were credited as instrumental in identifying the more efficient approach. The Oratomic team used an AI system called OpenEvolve to optimize their quantum algorithms, reducing the number of physical atoms needed to encode a single qubit by a factor of 100, a compression that fundamentally changes the scale of hardware required to mount a cryptographic attack. Cybersecurity researchers reacted immediately and in stark terms. Cloudflare, one of the largest internet security companies in the world, announced it was accelerating its own deadline to deploy quantum-resistant encryption to 2029, 6 years ahead of the timeline recommended by the United States National Institute of Standards and Technology. Google itself moved its internal quantum-safe migration deadline to the same year. One cybersecurity researcher at Cloudflare told Time magazine that the findings were a real shock, and that the industry would need to speed up considerably. Blivstein, a co-founder of Oratomic and one of the paper's authors, was more direct. He told Time that people in the know would understand that the threat was arriving, and that in his view the world was not currently prepared. It is important to be precise about what these papers did and did not claim. Neither Google's white paper nor Oratomic's research announced that anyone had actually broken any encryption. No password has been cracked, no bank account has been compromised, and no government communication has been intercepted by a quantum machine. The papers are theoretical resource estimates, calculating how many qubits a hypothetical future quantum computer would need to perform a specific cryptographic attack, and arguing that recent advances in qubit efficiency, error correction, and algorithm design have lowered that required qubit count more dramatically than previous estimates accounted for. Several independent experts who reviewed the Oratomic paper noted that some of its assumptions remain untested, and it will need to be validated as quantum hardware continues to develop, and they cautioned against treating the worst-case timeline as a certainty. The key phrase many researchers emphasize is that the hardware still has a long way to go because a 10,000 qubit machine capable of the coherence times and error rates needed for a cryptographic attack does not yet exist. What has changed is how far away that machine appears to be, and the answer is considerably closer than the field believed even a year ago. The threat that experts find most immediate is not a future attack on live encrypted data, but what security researchers call a store now decrypt later strategy. Adversaries with sufficient resources and motivation have been quietly collecting encrypted data for years, banking encrypted government communications, financial records, and sensitive corporate files with the expectation that a future quantum computer will eventually be able to decrypt them retroactively. If that timeline has genuinely shortened from decades to perhaps the end of this decade, then data stolen in the present under current encryption standards could become readable within a time frame that makes the theft strategically valuable in ways that assumed a much longer quantum gap. Security researchers have pointed out that many of the most sensitive categories of stored data, classified intelligence communications, long-term financial records, and private medical archives have secrecy lifetimes measured in decades, meaning the store now decrypt later threat is already relevant even before a cryptographically capable quantum computer actually exists. Governments and regulators have taken notice. The G7 group of leading industrialized nations has begun drafting roadmaps mandating adoption of post-quantum cryptography by 2030, and the financial sector has moved to the front of those conversations given its exposure to both long-term data sensitivity and the concentrated use of elliptic curve encryption in cryptocurrency protocols. Bitcoin and Ethereum both rely on elliptic curve cryptography to secure wallets and validate transactions, and the new research has fed a renewed and urgent debate within both communities about the timeline for migrating to quantum-resistant alternatives. Google's own white paper focused specifically on the vulnerability of elliptic curve cryptography used in cryptocurrency, estimating the resources a future quantum attack would require and arguing that the gap between those requirements and what near-future quantum hardware could plausibly achieve had narrowed enough to warrant treating the threat as a near-term engineering priority rather than a distant theoretical concern. The July 2026 update from Google Quantum AI added a further dimension to an already crowded year of quantum news. A new experiment demonstrated that machine learning could be used to monitor and adjust qubit performance in real time without interrupting running calculations, potentially addressing one of the most persistent practical obstacles to scaling quantum hardware. Every week of calculation time lost to recalibration represents wasted potential on a machine designed to operate under extraordinarily delicate conditions, and a system that can self-correct continuously rather than stopping to recalibrate represents a significant step toward the kind of sustained, reliable operation that real-world quantum applications will eventually require. Researchers working on the project describe the approach as teaching the machine to learn from its own errors rather than waiting for engineers to manually intervene, on a capability that would become increasingly important as quantum processors scale beyond a few hundred qubits into the thousands needed for practical fault-tolerant computation. The technique represents a convergence of artificial intelligence and quantum hardware that researchers believe will accelerate the development timeline for the next generation of processors, considerably beyond what purely hardware-driven improvements could achieve on their own. Taken together, the events of the past 12 months at Google Quantum AI trace something that looks like a genuine inflection point, rather than the incremental progress that has characterized most of the field's history since the first theoretical proposals for quantum computing were made in the 1980s, a verifiable proof that quantum hardware can solve real scientific problems faster than classical machines, a credible theoretical case that encryption could be broken sooner than anyone expected, and practical advances in keeping that hardware stable long enough to do useful work. These are not the same kind of milestone. They pull in different directions and carry different implications for different audiences. But arriving as close together as they did, each one building on the same underlying advances in qubit quality and algorithm design, they collectively represent a moment when quantum computing shifted in the public mind from a technology that was always coming to one that may already be here.